Okay, good morning, everybody. Thank you. Very good. There's always one. Now, who here is familiar with Bitcoin script? Put your hand up, please. Okay, who here is not? Okay, good. That's good. We've got some people. Okay, Christian is lying. Thank you. Okay, right. Now, okay. I wrote this whole thing assuming that everyone knew Bitcoin script, and then I went, oh, maybe they don't. So, in 12 seconds, I'm going to explain what Bitcoin script is. So you'll only be slightly lost for the rest of my talk. Okay, so Bitcoin script is a simple stack-based language. Every Bitcoin output has one attached. You give it a pile of stack elements, and then it's a little program. It contains opcodes to push things onto the stack, push things off the stack, add numbers, etc., right? You feed this program stack elements. If you feed it the right ones, it gives you the thumbs up and everything's good. If it fails or gives you the thumbs down, your transaction doesn't work, right? The most common script is simply to check a signature provided on the stack matches the transaction that we're spending. Okay, any questions? Good. Okay, with that out of the way, if I may, for the next 40 minutes, or perhaps we're down to 35 minutes, I would like to take you on a journey. If you don't want to go, that's cool. I suggest you just nap, because the next 4 days look to be pretty intense. But if you do travel with me, it's going to be a bit different, okay? I have the world's most boring slides. I didn't even use Midjourney once, right? Instead, the wonders that we're going to behold together will appear behind your own eyes. At best, I have some of the descriptions that I might have used to prompt images, but I'm cutting out the middleman and feeding them straight into your imagination, okay? So let's begin. One of the original opcodes, Bitcoin opcodes, was disabled in version 0.3.1 in 2010. There's the CVE number. Okay. It's recently been reproposed by many people, including Ethan Heilman, but with a 520 byte restriction. Now this makes sense because you're not allowed to start with any stack elements greater than 520 bytes. So if you cut Opcat so it can't produce them, you're consistent, but it does feel limiting, right? The obvious problem with this is that if you don't restrict it, right, you end up with Opcat, dup, Opcat, etc., until your machine blows up, right? But you can fix the obvious problem here by having a total stack limit. You were allowed to have 1,520 byte stack elements, so let's just say you can have up to 1,000 stack elements, and the total number of bytes could be 520,000. Okay, so we fixed that. But then you hit another problem. Let's look at this little script here. Opdup, OpSHA-256, opdrop. If you have 4 megabytes worth of this, you're basically duplicating the top entry, hashing it, and then throwing it away again and again and again. So while we've solved the memory problem with a total stack limit, that leaves this problem. So if you max out the stack in our proposal, you could do 260K because you dump it for a total of 520. And on the left is what happens if you have a 4 meg script that does this with 520 byte. You can't even see a bump there, but there is one. It's a couple of seconds. If you have 260K, that is the image on the right. And you can see a full block of those takes 700 odd seconds. This is what we call in engineering bad. Now, part of the problem is opdup, which makes a gratuitous copy, and you can fix that fairly trivially. But we get a little bit better, maybe. You know, but this is still bad. Okay, so this is kind of similar to a problem we already have in Bitcoin, which is that checksig operations are slow, and Taproot solves this with a sigops budget. You know, you basically get 1 opchecksig per 50 bytes of script, right? You go over that, your script fails. You're doing something weird. So, obvious question. Can we do the same thing with a hashing budget? The TapScript sigops budget works because it's generous enough that you don't have to worry about it, but low enough that it prevents you from DOSing the network. Can we do the same thing here? Okay, well, this is the question. Let me show you another little script. Opdup, op equal verify. Duplicate it twice, check that it's equal. It should be, of course. You can also fill 4 megabytes of this. And actually, it's still pretty bad. There's no hashing in here anywhere. Okay, so it turns out that it is not just hashing. On modern CPUs, SHA-256 just isn't that slow. It's also hyper-optimized in Bitcoin because we use it everywhere. Now, once you restore larger stack elements, the question now becomes, what's the worst case stack bytes actually touched by a reasonable implementation? Okay, so the budget cost should depend on the size. This leads us to what I call a VOPS cost model, right? It turns out all our operations which work on a stack, because we're a stack machine, basically can be expressed as linear passes across that data. And that's sensible because that's how modern machines work. It's how caching works, right? If you cache something, your cache loves you when you access it nice and linearly, and all of them do that. We can basically assume that that cost dominates, right? We don't care about actually resizing the stack itself. We don't really care about whether you're doing a read or a write or modify. That's all good. We assume that we're using simple arrays and vectors, which we do currently. And we assume that anything you're doing with the things in your CPU is basically free, except for hashing. Okay. And this is important. You have to think about the worst case. How bad can it get? How much accesses do you need to do in the worst case of the data? If you do this, let's see what we get. Here's opverify. Opverify says, is this 0? If it is, fail. Okay. Now, the cost of this, you have to look through the whole thing. I mean, it could be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, right? It might have to go 520K to find whether it's 0 or not. So the cost is simply the length. Straightforward. 520K of reads. Opt-up, a little bit different. You make a copy. Read, write, read, write, read, write. Operand length times 2. Okay, so far our model looks good. Let's look at op equal. This one's a little bit weird. It's either free, because if the lengths are unequal, you don't even need to look at them. You go, they're not equal, I know that. Or it's the length, which is both of them, times 2. So the cost isn't actually a linear function necessarily of your sizes. We can do this for every push opcode. For push, you're kind of copying out of your data stream. So you can technically pay the cost to write it on the stack. Okay, that's fine. Everything else, you know, how much data did you copy? Twice that is your number. Okay, this is good. Verify again, equal verify, ifed up. You should note that there's no VOPS table for op-if and op-not-if, and that's because in Taproot, they have to be 0 or 1. You're not allowed to put 520K on the stack and say, is that true, with op-if or not-if. But ifed up doesn't have that. Okay. Now, hashing. We talked about hashing. And for that, it's length times by some hash factor. Right? So, because hashing is one of those cases where our assumption doesn't hold. You do actually spend some CPU churning through the data, so you can't just go memory bound. And we see here this hash 256, which is hashing it twice. We don't care. That's an edge condition, right? We care about really big data, in which case doing one extra hashing is in the noise. Okay. And there are 2 old hash opcodes, RIPEMD 160 and SHA-1. Nobody's going to optimize those. I don't want them to have to do it. So you just fail. If that's too big, you fail. And you start to question your life choices if you ever hit that condition. Because why are you doing that? Okay, now the hash factor I mentioned is to be derived later. And we'll see that in a later slide. Okay. So we have our model. And this constrains our worst case behavior. So let's restore some opcodes now, okay? Let's start with the bitwise ones. Op-invert flips every bit. Well, the cost is obviously the length, that's easy. Op-and is the sum of the 2 lengths, whereas op-XOR is double the minimum of the shortest one. With OR and XOR, you presume that you're operating into your longer one, right? You're flipping the bits. You XOR, and then if you run out of the short one, you just stop. With AND, you've got to zero out everything else. So AND is the sum of the 2, and OR and XOR are slightly cheaper. Okay, cool. Now Upcat itself, remember where we started with me getting upset about Upcat being limited? Well, let's look at it. If it simply allocates a new vector and copies them both in, it looks like this. The cost is obviously copying both of them, twice the input length sum. But that is not how you implement Opcat, right? Any programmer will tell you what you actually do is you resize in place and then copy, because you're hoping the resize in place is basically free. But that turns out to be the same cost. And the reason is, in the worst case, that reallocate in place will have to do a copy internally anyway. So it's the same number, right? Remember, you're always allowed to beat the model. You can do smart things in certain cases and completely outstrip the model. That is fantastic. You're doing really well. Faster is always better. But you can't make the worst case worse. Okay. Let's do the other string opcodes while we're here. Left and right. Left is easy. It's basically free. You do have to read the offset. Don't forget that the number of bits that you're supposed to, or number of bytes you're supposed to cut at, that could be 520K long, right? Because it just could have a whole heap of zeros in it. So you do have to read that. But once you've done that, you just chop. You don't touch any data at all. Right is a bit different. You have to move the data down to the front. By the way, left and right do exactly what you expect. They cut at certain points. You take the left part, or you take the right part. Okay, so right's a bit weird. Take the length, minus however much you said, whatever offset you said, and that's the amount. Technically, that's bottom to 0, but you'll figure that out. Substring is basically they tell how much to copy out of the middle. The cost is effectively the amount that they tell you to copy. Great, okay. Now we're going to get to two of my least favorite opcodes. L shift shifts a value to the right, and R shift shifts a value to the left. Thank you, little endian. Okay, so I have renamed these to upshift and downshift so we sound vaguely coherent, okay? Downshift has to just move some bits from the end to the start. So it's pretty straightforward. You basically go, how many bytes are you actually moving? You've got to read the value. You've got to figure out how much you're moving. That's fine. Upshift, however, upshift has two distinct cases. And I'm still going back and forth whether we should split these, but you're either moving a whole number of bytes, which is easy. It's basically just a mem move. It's basically that you allocate and you just shove stuff into the front. Or you have to allocate, shove stuff into the front, and then add 1 byte at the end and shift everything along, which means another pass through. So it's 4 times the value. So that's kind of ugly, and the names are terrible. Now, unlike the L shift and R shift, which was in 0.3.0, these versions do not trim the trailing zeros. Satoshi's implementation did. So they turned them into numbers, which means they shift they trim the trailing zeros, because trailing in little endian means the big ones, right? So instead of 00001, you end up with just 1. We don't do that, because that's an interesting design choice for shifting. Okay, okay. That did get ugly for a moment, but we're through. We have unshackled our stack limits. We've restored our opcodes. What else is there to do? Well, script is limited to signed 31-bit arithmetic. But we can have up to 51 bits of Satoshis, right? I can't, but in theory, someone can. Actually, I'm quite happy with 31 bits of Satoshis if anyone wants to help me test. And there are also other unsigned 32-bit fields that we'd like to deal with, right? Now, Blockstream's Elements has a whole suite of opcodes to do this, right? It has these 64-bit opcodes. It has conversions back and forth between the 31-bit script numbers we have today and those. And every time, when you add or subtract values on the stack, you get 2 values. You get the value and a flag that says whether it succeeded or not, whether it overflowed, right? Now, this approach makes me a little bit skeptical. Firstly, because it's ugly. You end up basically doing op verify after every single arithmetic operation. But also because my first computer was 8-bit. Well, it was kind of like, it had pretensions of being 16-bit, but really it was 8-bit in 16-bit pants. And then I went through a 32-bit transition, and then I went through a 64-bit transition. So I just have a feeling that I cannot guarantee you that 64 bits will be enough forever. And at this point, I'm looking at my VOPS hammer and going, what if add simply doesn't overflow? Right? What if we just go, well, variable length integers, right? Now, one of the problems with variable length integers is where do you put the sign bit? And the answer is don't. Everything is unsigned. And we should define all our arithmetic ops to normalize to truncate unnecessary zeros. If we do this, we end up with something that looks like this. Here's how much everything costs. Op negate and op abs are unused. There doesn't even make any sense anymore. We don't have signed things. So potentially 2 more op success opcodes. But every other comparison is pretty much exactly what you'd expect, right? This is straightforward. Okay, well, that's cool. Subtraction is fun. We have no negative numbers, so it can fail. And I thought about doing this element style push the success flag, but I know you're just going to do op verify after it every single time. So let's just do that directly. You're not allowed to underflow. It fails. If you really want to do that, dup2, do your comparison first, check, but you don't. So we do have to. It's fairly straightforward. It's the sum of the 2 lengths. You're basically subtracting everything. In worst case, you subtract something and you have to go all the way through because it underflows all the way through. But that's OK. This does assume that you subtract in place, by the way. You're not subtracting to a third thing because that's 3 passes, not 2. But that's fine. Yep. Now, but we do define it to normalize. Remember I said we might as well trim zeros. Arithmetic op should trim zeros. That just makes perfect sense. We do that today. But you can't do it in the naive way. You can't do the subtraction and then walk back through it to find how many zeros are and chop it off. Because that would be a third pass. And the model doesn't allow that. You're only allowed 2. But that's easy. What you do is you just track the zeros as you go. If you put a 0 there last, you remember, and then you go, OK, that's fine. Add. Can we add? Yes. Well, it's just like subtract, except it can overflow. And if it overflows, worst case, you have to add a byte, which means you have to reallocate the whole thing, which means another copy, which costs you twice the length. So worst case, it's basically 4 times. So it's twice as slow as add. But it works in the model. OK, here's our costs. We're all good. OK, it's a lot of talk. This is a good time to show you some actual benchmarks. I had to actually implement this, right? Partially to test the model, but also to get a feel for what's performance like. You know, I've used 520 kilobyte opcodes, operands, which I know I said that's the total stack limit, so actually you can't have 2 of those and add them together, but just bear with me for a moment. I wanted to compare apples to apples. Here is the implementation. Now this matters, right? The blue one on the left, the columns on the left, are the naive, byte by byte, stupidest possible implementation you can have. We won't be doing that. The second, the middle column, is what happens if you have unaligned vectors. Nobody has unaligned vectors. Don't do that either. But it's important to handle it if you have it. And then on the right, that kind of cream-colored column, that is what the actual performance you get. This is on my laptop anyway. On the far end, I put SHA-256. Remember our SHA-256 friend? That is doing a whole SHA on 520K. And it turns out that's about 8 times as expensive as doing an invert. So that's where the number 8 comes from. So that means that this would work on my laptop. OK. All right. We've done that. Let's bring back some other opcodes. Opmul, let's multiply. It's basically a series of adds, right? Now, at this point, you go, how many adds? Well, the answer is how many, what's your bit width? Everyone is 64-bit these days, right? So I can just assume that. You have a 64-bit multiply. Even ARM, even Raspberry Pis, now have a 64-bit multiply in hardware because of Neon, right? So every machine you're likely to run on, every machine you can pretty much run Bitcoin on reasonably today can handle 64-bit multiply. So that's easy. You do that. You can do better than this naive add. There's Karatsuba, there's Tom Cook, there's FFTs, there's the whole thing. But I do not assume that our implementation will do that. If somebody does, they'll beat the model, and that is wonderful for them. I looked at libGMP. It is so fast. It's unbelievably fast. But it has about 8 to 12 different multiplication routines, depending on which sizes you're dealing with, and we do not want to do that. I do not want to do that. Somebody else can do it. I have not done opdivide. It's kind of the final boss of variable length arithmetic, and it is on my to-do. I have. They will stay tuned for that. OK. We've got our VOPS things now. We know a cost for every thing that we could do in script, and we've used it to free us from the shackles of small size limits, right? But we didn't actually discuss how much budget do I get? How much budget do I start with that I'm going to take this from, right? How much VOPS budget do you get per byte? That is actually not a trivial question to answer, but we do allow 80,000 objectives per block, right? How long does that take? Well, on my laptop, it takes 4.92 seconds. And during that time, I could do about, what, 35 gig of op inverts. And so I blocked all that. Therefore, the answer is 8825. Right? So this is my penciled in number for that multiplication factor. For every byte, you will get 8,825 VOPS budget to play with. But when you think about it, you could have your 80,000 check sigs wasting that much time, and then you could use up your entire VOPS budget and waste that much time as well. Again, doubling your block validation time, right? So really, it makes sense to combine this into one budget again and go, well, whatever you get for 50 bytes, you can do a check sig, and will come out of the same budget, right? So we unify the budgets at that point. Now this is important. To look forward a little bit and presage later on in my talk, if we have introspection opcodes, okay, if we have more advanced introspection opcodes, certainly, then the budget should be per transaction, because a script can ask about the other inputs or the other outputs. And it's not your fault if you're a small script. What you care about is the size of the transaction. So the budget actually depends on your total transaction size, not your individual witness weight, which is a change from the way that the SIGOPS budget works. Okay, how would we transition? And I had to redo this slide yesterday because we had a discussion about this and everyone hated the way I transitioned. I added a new SegWit version, BT1Z, but everyone went, you don't need to do that, Rusty. They suggested that they really want a 33-byte script pub key because they want the parity bit back, because apparently it just makes life really hard to do 32-byte X-only pub keys. So if they did that, we could say, okay, in that case, you're using new script. Because we want to reuse existing opcodes and change the number semantics, it would be awkward just to add a crap load of new opcodes. Add V, add sub V, sub 1V, all those. If we want to change opcode semantics, we really do need to update the script version to be TypeScript v2, internally at least. But we also want to avoid this dummy key penalty, right? So if you use Taproot today and you only want a script, you put in a dummy pub key. And that seemed like a good idea at the time, except the problem is that every time you propose a new opcode, everyone who wants to use it goes, but it's going to cost me 33 bytes, because now I have to use Taproot, and there's no particularly good reason for that. So it would be nice to define it such that you can omit that. And there was a whole discussion yesterday on how we could do that. But basically, you either have a raw Merkle sum in there, or you use a dummy nums point. It also, frankly, makes writing the script interpreter a lot clearer. You know, if you're this, you use these versions, otherwise this. So that's nice. Okay. At this point in our journey, we have climbed mountains, you know, crossed rivers, battled dragons, well, cats. We battled cats. They've got claws. That's like a. Okay, imagination. We have battled dragons. Let's stick with that. We seem to have a way to place reasonable limits on the 51 opcodes that deal with variable length stuff in script. Many of the restored ones in a way that doesn't actually seem too onerous. Right? It's pretty compatible with stuff that we do already. So at this point, I want to look briefly into the future. Okay. There we go. Why did I not just break this up? Okay. It's worth noting, Upcat by itself, and certainly the other opcodes, give us covenants badly, right? Right? We've got them badly. And now we can handle values nicely. We can actually deal with 64-bit values in the same way and everything else. It seems obvious that let's just give ourselves direct introspection. Let's just ask, what is the value of this? But I want to make a very good point here that that is not sufficient. And I will give you a thought, like kind of a thought experiment on why you can't just live with VOPS über alles. Okay, it's not all we need. Let's take a look at the great-granddaddy OG introspection opcode called OpChecksig. Or to give it its scientific name, op select TX parts from flags, SHA-256, and checksig, right? Now imagine you're like a VOPS maximalist, and you're like, you know what? We can deconstruct this and have a script that looks something like this. You know, it gives us the bits of the transactions, and then we share it ourselves. We hash it ourselves, and then we OpChecksig from stack. It's the stupidest name ever. Of course, from stack. We're a stack machine. Everything's from stack. But you know, just to differentiate from the other one. Okay, so we could have a 4 megabyte transaction. It could have, containing this script, about 38,000 inputs, each of which would try to hash the entire transaction. The cost, according to our cost model of that, is about 35 times the budget that we have. Right? Each input is hashing the entire transaction, 4 megabytes, over and over and over again. Right? So obviously, you can see from this that that is grossly inefficient and exceeds our budget, even though our budget is incredibly generous. Right? Which is another way of saying the same thing. It's too slow. And it's stupid. They're all doing exactly the same hashing. We need some kind of introspection which gives us a cached hash that has been calculated once for the entire transaction and things like that. We need this to make this work. You can't just use VOPS. Okay. Now Bitcoin has changed a bit since 2010, you may have noticed. But two things particularly stand out. We've added taproot trees and we've added op success. Op success is fantastic because it's mere presence in a script. Just being there makes the script succeed. And taproot trees allows you to specify a number of conditions and meet only one of them. Fantastic. But this presents a problem for introspection. You see, if you want to say this script, I don't care what it does, but it has to test condition X. It has to be a 20 block delay or whatever else, and then whatever else you want. You can't do this. You see, you can't use separate taproot leaves because they provide an or. You want an and. You want to say this condition and something else. And you can't do the obvious thing and go, well, as long as your script starts with 16 op CLTV, then I'm happy, because they can stick an op success later on, and the whole thing will succeed without running that at all. So one way of solving this is to produce something like an opcode like op segment. It does exactly what it sounds. You scan the script, you divide it up along the op segment divisors, and you treat each section of the script separately. You look at the first section, you go, it has no op success in it. You evaluate that. You look for the second one, you go, oh, it has an op success, we succeed. Or it doesn't, and we evaluate it, right? This effectively prevents an op success override in a certain subset and allows you to do this and condition and say the script must do this. Okay, cool. Obviously also, because of the way taproot trees work, you effectively, in order to prove the root, you will need to be able to tweak. Do an operation where you take a key and you tweak it with a value. That's one of the fundamentals that we require. The minimum thing would be to implement that as an opcode. It's actually surprisingly slow. It's not quite as bad as a signature check, but it's slower than I expected. And because taproot trees are sorted lexicographically, that turns out to be exactly the opposite of what we do, because we're a little endian. So you do need some way of doing a bit 341 style compare. The best way I can think of to do that is have a byte reverse that switches your endian. So you can switch the endian of the two of them and do a compare like normal. We could change that, but we were not going to. And of course, while you're here, let's get OpChecksig from stack. I want to call OpChecksig and rename OpChecksig, but that's probably a stretch too far. But it is trivial to implement and very easy. And it does deconstruct stripped a little bit. Okay. Now let's go further in the future. What else could we want? If we want script to be this grown-up cat that does everything we could ever want, what else do you want? You want iteration. No, not that kind. You actually just want. What you want is an op each input and an op each output. You want to be able to say, oh, I want to do this for every input, or I want to do this for every output. It's very natural. It's very constrained. It pushes the input number on the stack, runs up until the next op end if. You probably want op break and op continue. What's interesting is you can pre-process this, right? You can say, oh, I can expand this out. Because at the time you're looking at the script, you know how many inputs and outputs there are. So you can actually just expand it out into a bigger script that has this cut and paste over and over again. It does mean weirdly that the weight of the script now depends on the number of inputs and outputs, which is just odd. But it does work in some way. And I am only suggesting this because even the mental model of this existing proves to be useful. So even if we never actually implement OpChe input and OpChe output, they turn out to be very powerful tools to evaluate other things. And we'll see that in a moment. OK, now, I don't know if you're paying attention, but fees are going to go up. That was actually a controversial statement a number of years ago, but now it's widely accepted. What does that mean? Well, it has a whole heap of side effects. And it has side effects on the design of scripting, interestingly enough, because people will do an obscene amount of engineering in the future to avoid paying fees, because it will be worthwhile. OK. Every multi-party scheme that I'm aware of involves basically holding a transaction from your counterparty ready to go should things mess up and going on chain. And holding it for a significant length of time, potentially. That means that you don't know what fees are going to be. You really want to add fees later. And the way everyone does this is child pays for parent. They just throw another transaction in, right? Now, the problem with that is, remember, fees are going to be expensive. And there's certainly a strong argument to suggest that the way you'll get around that is directly paying a miner, because you don't want to pay a whole other transaction, but directly paying a miner is a genuine centralization force, because you will pay the biggest miner you can find. So the bigger miners will be more profitable, right? And it doesn't matter, actually, whether you're doing that through a CPFP or you're just adding fee inputs and outputs later. They're still expensive. Fees are expensive. You're going to look at it any way you can to reduce them. And that, if that drives centralization, so be it. You won't care, because your transaction will get in. OK. However, if a transaction can have these bundles, then in theory, you could take a whole pile of these transactions, stack them together, and add a single fee to the whole lot, and amortize the cost of this fee. How would you do this? Well, I have one design, which you could certainly poke holes in. You would basically, at the end of your sub-transaction, you would mark it end of inputs and end of outputs. You'd put something in somewhere. If we have 33-bit script pub keys, you get a few spare bits. You could chuck one in to say, this is the end of my little stack. And of course, this would alter the semantics of iteration, check, sig, and introspection. They would all behave as if you were the only thing in the universe. Your substack, your little sub-transaction was the whole thing. So those all just worked like normal. And of course, if there's no end marker, that means your group is the entire transaction. So that's where you stick the fees at the end. Right? That would kind of work. So basically, you could have someone out there who you throw some sats at, throw them in your transaction, they just stack them all together, and they attach a fee output. And anyone could do this. Yes, it is trusted, but it doesn't have to be a miner doing this. Anyone could throw transactions together for you, take a fee. And it's kind of a recurring service, too. So there is some reputation that would work in this case. And of course, if all else fails, you just do it yourself. Your stack of one, you add your fee, but that's obviously something you don't want to do all the time. But there's another really interesting idea which competes with this, which came out recently, so I've put it on here. And that is this idea of the Ruben Merch neighbor sponsorship, where the transaction can say, I am only valid if I immediately follow this other transaction, right? Which is kind of like and you can do that pretty cheaply. And if you could do that for several hundred, rather than stacking transactions, you would just turn them into this road train of transactions. And right at the end, you would have your sponsor that's paying for everything else. We went around way too long yesterday on this. It does end up costing you about 40 more weight per sub-transaction to do sponsorship. It's slightly more efficient to do stacking, but you could also argue it's more work to do stacking. So I'm leaving this one open. Just wanted to make sure everybody knew that we were going to have to do something along these lines so that we can handle the fee issue. Okay, there's a whole pile of bike sheds to paint and to-dos. I said the total stack limit, 520K, is obvious because it doesn't change anything. But I can't find anyone who knows. Does anyone know why the limit is currently 520 bytes per stack element? Yeah, why 520? Right, yeah. Oh. Right. Okay. That's the best one. That's better than the 8-byte prefix on a 512-byte pile of poop. Okay, yeah, I'm gonna go with that one. RSA, so Andrew Polstra suggested that there's a hypothesized reason that you can fit an RSA signature in there, which is true. And that in some pre-Bitcoin, they could have used RSA, and hence that. You can see the bones of that design carried through in the 520-byte limit. The truth is nobody truthfully knows why 520 bytes, so it's kind of arbitrary. And arbitrary limits are annoying. Since we have a SIG-ops budget, or we have an ops budget now, we could unleash that a bit. And we could say, well, a transaction can be up to 4 megabytes. You can have 4 megabytes on the stack. It means you can drop a whole transaction on the stack. We should probably add a little bit more so you've got a few other things. But, you know, for genuine megabytes, not for a million bytes, would be a reasonable stack limit. It does increase the runtime requirements of your Bitcoin node, but nobody cares. Like 4 megabytes is not going to cut the difference, right? So we could certainly have that debate. Wider benchmarks, right? My laptop's not a canonical thing to use. We do need a broad range of benchmarks to establish relative costs across a whole heap of different machines. I've got to implement opdiv. We do need a full script implementation, right? We actually need not just enough for me to benchmark. I tended to mug op and op4 for different things so I could benchmark it. You actually need to write the code and do it properly. And then you're like, well, what other changes, right? What introspection opcode? I said we should have one. It'd be nice to have one. We need to be able to see inside our things properly because we can do it badly, so let's do it well. You know, but there's a whole question of like, while we're here, what else should we do? That is a whole thing that basically is the next 4 days of talks. What other things could we do? And I only have 45 minutes, so we're almost at the end. Summary. So when I suggested that I hated 64-bit arithmetic, well, that rather than 64-bit arithmetic, we should go for variable length arithmetic, Anthony Towns pointed out to me that actually, this is a return to Bitcoin 0.3.0. I hadn't realized. I knew all the opcodes had been thrown away, but I didn't realize that originally we had variable length integers in Bitcoin. More broadly, the script system that we ended up with after the emergency response to the CVE, when everything was on fire, is like this strange, awkward thing, right? Not the programmable money that we all envisaged. But a full restoration of script does more than bring back something that we lost. It lets us evaluate ideas. Iteration, segmentation, these are ideas that came around because people wanted to make vaults, right? And new ideas are much more powerful and concrete and able to be assessed and evaluated when you can express them in script itself. And then if the new idea is useful and you can't do it in script, why can't script do it? Why don't we fix script? So, and finally, script, being its full self, lets us evaluate future optimizations, right? We can see how much it would improve based on real usage, right? And don't worry, there's still going to be plenty of things we can argue about. But if someone proposes a new opcode, even if you would never use it, you can see how much it would optimize on-chain usage that other people are doing and leave more room in blocks for stuff that you do want to do, right? And in the extreme case, we can even consider new key types. If there's some script that everyone's using, we can go, cool, let's just make that a new key type. And it expands internally to that script, right? In the next 4 days, you're going to hear some amazing ideas. And I've spent my entire 30-year programming career building tools for other developers to build things that I can hardly imagine. And sometimes they've been stupid, and sometimes they've even been evil, but the vast majority of them are brilliant and fantastic. And I can't consider that we would want to do anything short of giving them the best possible tools that we can build. Now, we need to put in the work, and it needs to be thoughtful, and it needs to be thorough, and it needs to be methodical. But nothing here is novel or even conceptually complex. It's just engineering. And we've done much harder things in Bitcoin already. Now, if my own children should take an interest in Bitcoin one day, I hope they get to control their own money. And I want doing that to be as natural and expressive as it can be. And if you feel the same way, I hope you'll continue this journey with me. Thank you.